Welcome to Physics 4A Problem Solving Companion 9. In this video, we extend our mechanical approach to situations that involve rotational motion of extended rigid bodies. This companion video is paired with Physics 4A Lecture 16, Intro to Torque and Rotation, and Physics 4A Lecture 17, Rotational Inertia, Kinetic Energy, and more. And you may also see topics covered in the optional lecture. Physics 4A, Lecture 18, Optional Rigid Body Motion topics, including precession. In some sense, many of these questions should seem familiar using standard strategy and conservation law problem-solving strategies. What is new here is the additional, realistic complications added through rotational motion of objects interacting. Following are the sections in this video. All the chapter and problem number references are for OpenStax University Physics, Volume 1. First, a way to extend the pre-derived rotational inertia formulas. Rotational inertia by superposition, working out Chapter 10, Problem 56. Then we get started with dynamics, rolling dynamics, remembering friction, working out Chapter 11, Problem 23. And next, rolling kinetic energies, working out Chapter 11, Problem 28. Cross product for torque and angular momentum, working out Chapter 10, Problem 82, and Chapter 11, Problem 34. Angular momentum conservation with changing I, working out Chapter 11, Problem 52. Bug rod collision, L and TE conservation with SageMath, Chapter 11, Problem 98. We will start with the rotational inertia question. All right, so let me look at this question. So it says, calculate the rotational kinetic energy of some mass, motorcycle wheel. If its angular velocity is okay, we're given the angular velocity, and it's, oh, I see, inner radius, let me label this R1, and outer radius this R2. So if you're thinking of a motorcycle wheel, it's a geometry, then I hope you have this image in mind of some circular disc-like object. And it's not just a ring, and it's also not a solid disc. It's a donut, which is why they are giving you a set of two radii. So this is my inner radius, R1, and this is the outer radius, R2. And looking at it, so in this question, they didn't give you the rotational inertia. So rotational inertia is one of the things that you will have to find in the course of answering a question like this. And they are asking for rotational kinetic energy. I think I have the formula memorized for kinetic energy, or from having the translational kinetic energy memorized, which is 1/2 mass times velocity squared. I can guess from the analogy that rotational kinetic energy will be 1/2 times the rotational analogy of mass, rotational inertia, times the rotational analogy of velocity, angular velocity squared. So since they're giving us the angular velocity, really the only thing I need is the rotational inertia. So that's the crux of this question. So when you have to work with the rotational inertia, you are always, of course, welcome to look up the textbook for for what rotational inertia for the particular geometry is. And in the lecture, I did go over deriving rotational inertia for certain particular geometries. In general, I would say, feel free to look it up from the textbook. First of all, know where to look it up from. I think it's in under fixed axis rotation, and I think it's gonna be under calculating moments of inertia. So let's scroll down and see the method, yeah, which we covered in lecture. And using these methods, you can. Do they have the table? No. All right. It's in the other section. 10.4. Moments of inertia and rotational. Sorry, it just doesn't make too much sense to me. So they gave you this table of rotation inertia and then told you how to drive it. All right. Now, as you look at this table, you are going to. Oh, so in this particular case, I guess you could use this rotational inertia. So uh, that wasn't the way I was going to go, but you know what? That is in the textbook. You are welcome to use it. So this is the formula for rotational inertia for the kind of object that's described in this question, which is it's like a disk. So if it had been disk, you'd have been looking at this formula here. Solid cylinder, except the height is very thin, so that it's just a disk. For this axis, that height doesn't matter anyway. So it's like a disk, except you have a center hollowed out. So, if you want to use this formula, let me just quickly work out the answer, see what the answer is. And then I will do it one more time the long way. And just to verify that the long way, which I think is conceptually more grounded, gives you the same answer, the same correct answer. So with all these things I have looked up, this is what I can do. I can say, all right, let me declare some variables I'm gonna use for number plugging in exercise. I need my mass. I need my omega. I think that's everything I need. Yeah. So my kinetic energy. Oops, kinetic energy is going to be 1/2 times rotational inertia, which comes from this formula, mass divided by 2 times R1 squared plus R2 squared times omega squared. So that's my kinetic energy. And to get the numerical value to plug in, I use the substitution syntax to plug in the numbers. My my mass is 10 kilograms. I'm just going to use basic SI unit. My R1 is 0.28 meters. My R2 is 0.33 meters. And if you are worried about these being interchangeable worries you, don't worry about it for now. Let's see what answer we get. I need omega. Omega is radians per second is the basic SI unit, so I'm gonna put it in that exact unit, 116. Okay, so with all those, the number I get is 6,301. So this should be in basic SI unit, so joule. Let's just give it a try, see if that's the correct answer first. And yeah, it's the correct answer. I didn't really have a big doubt. And let me show you give you an alternate scenario. What if the table of rotational inertias you are looking up isn't as complete as this list? This list has 10 different geometries. What if the list you're looking at has smaller set of geometries? I can imagine this not being given on some of the tables of rotational inertia. What if we have that? That is the scenario where the approach I'm going to describe is going to be very useful to help you make use of the knowledge that you already have. Because, so even though this geometry is not quite as common, so you can imagine that not being present in some of the tables you might look up, I would tell you the rotational inertia of a solid disk. It's one you can rely on having either on a table of rotational inertias or, frankly, this is one you should have memorized. That would have been my recommendation. Memorize rotational inertia for a solid disk so that when you have a question like this one, you can use the approach that I'm going to describe. So you are looking at this object where it's a donut or annulus or whatever. It's a combination of two circles basically. There's an outer circle, there's an inner circle, and inner circle is the whole. And as you look at it, if this was made instead of two parts, then you could describe it in terms of a solid cylinder of a cylindrical axis. So the two parts one wishes, one could describe this as is this part of radius r2 that is a solid disk. So one that's just completely filled from radius equals 0 to radius outer end. And somehow, if you could subtract off a smaller circle or smaller disk of radius r1 that is also solid and has the same density as the bigger disk, then that would give you this shape. And what I'm here to tell you is yes, you can do that. And I guess if the fact that you can do that makes intuitive sense to you, then great. Go ahead and use it. I've told you you can do it. Go ahead and do it. Somehow, if you need a justification why this should be possible, the justification I would cite is something called the superposition principle. This is something you are going to see more in the future. In your math class, potentially in your linear algebra class, and in future physics and engineering classes. This is a principle that holds. Let me describe it this way: holds with linear systems. And I will leave the more precise definition of what linear means to your math class and future physics and engineering classes. For the purpose of this question and for our purposes right now, we'll just say we're going to use the superposition principle to derive the rotational inertia of the wheel. So we'll say rotational inertia of the wheel is going to be rotational inertia of, let me call this 2, minus rotational inertia of this piece 1. So I2 minus I1, by which we would mean, using this formula here, and being careful that the mass that is referred to here is the mass of the object. So I gotta give it symbols to make sure I won't accidentally write down the wrong thing. So this says mass M2, and this is going to have mass M1. So the combined rotational inertia would be 1 half, that's the 1 half there, mass 2 times R2 squared minus 1 half m1 r1 squared. Okay, and if you're looking at this minus sign here and you're looking at that plus sign we had before, and if that makes you worry, don't worry. Let's just continue through the derivation because we're not quite yet done. For one, we have too many unknowns. We got these unknowns m2 and m1, and frankly the information that's given to us, it's neither of those. We are given the mass of the wheel, which is mass of the wheel. So let me call the capital M, which I guess thinking through this superposition principle, it would be really M2 minus M1. So, okay. So let's think of a way to write this out. So for this superposition principle to hold, really what we need to be able to say is we need to be able to say that for these both of these objects, densities are the same. Which so we haven't technically covered the densities yet, but I think you can get some intuitive sense of what we are going to use as our operational definition of density for this question as being the total mass, for example, M2, divided by the total area. So that would be pi r2 squared. So what we are saying is this is same as m1 divided by pi r1 squared. Okay, so with this expression, let's do this. I'm going to see if I can. Let's try eliminating m1 and see what that does. So solving this for m1, I have pi's cancel. Good. um, m1 is equal to r1 squared over r2 squared times m2. Okay, let me plug that in. Then I have an expression for rotational inertia of the wheel of 1/2 times um, m2 r, right, this one doesn't change, minus, and here it let me do a little bit of simplification as we go. So I'm gonna plug in m2, so it'll be minus 1/2 m2 times, and oh wait, I can't simplify, never mind. So it's going to be r1 squared over r2 squared times r1 squared. All right. Okay. Now we are not given the m2. Um, what we are really given is the mass m here. So let me see if I can somehow simplify this down so that our expression here is going to be in terms of m. I think I can do the same thing I did here by plugging in mass m1 here. So plugging in the expression for m1 up to here, I have m2 times, and I'm gonna imagine factoring out m2. Then I have 1 minus and r1 squared over r2 squared. All right, let me see. So solving this expression for m2, this is what I'm gonna have. I'm going to have m2 is equal to total mass m of the wheel divided by 1 minus r1 squared over r2 squared. Just scroll up to double check. Yep, they match. Good. So all right, let me plug this in and just let's see what comes out. Maybe something good will happen. Maybe nothing good will happen. We'll see. So rotational inertia of the wheel is, um, let me just factor out some of the common. Do I want to factor out? Yeah, let me do some intermediate simplification. I can see that 1/2 is in all the terms. So I'm going to factor that out, 1/2. And I see m2 is in both terms. So I'm going to factor it out first and then substitute this in. So it's going to be m divided by 1 minus r1 squared over r2 squared times, and the rest of the stuff that didn't get factored out, that's going to be r2 squared minus r1 um, r1 to the fourth power. Let me not write it that way. Let's see. Let me try writing r1 squared times another r1 squared over r2 squared. All right. Let me do this simplification. I don't like seeing all these nested fractions, fraction of fraction. So one way you can get rid of the nested fraction is by doing this, by multiplying on the everything on the numerator by r2 squared and everything on the denominator by another r2 squared. Um, then on the just writing out the whole fraction thing all over. So I have so this is this ratio is 1. That's why I can do it, because it doesn't actually change any quantity. So multiplying this in, so I can absorb this factor into one of the two parentheses. So I can absorb this into here. So then I'll have 1/2 mass divided by r2 squared minus r1 squared times, and I can absorb this numerator thing into here, which will give me r2 to the fourth power. Okay, okay. I think it's gonna work out. Okay, minus I have r1 to the fourth power, and normally, so this r2 squared, it's getting distributed into these two terms, and the r2 squared getting multiplied to the second term, it cancels out this denominator. So I'm good. I think this is it. So if you want, you can end things here. This is your expression for rotational inertia, and we can see how the overall answer works out with this expression for rotational inertia. Let's just make sure that numerically this is correct. So my rotational kinetic energy, we'll say it's the value of the rotational inertia here, which will be everything here. So let's say 1/2 times mass divided by r2 squared minus r1 squared times r2 to the fourth power minus r1 to the fourth power. Okay, that's all over rotational inertia. And if we let me just display kinetic energy expression to make sure I actually changed it. And then when I substitute in these same values, you'll see that it's the same number. So this is the correct expression. If you want to leave things here, that's perfectly fine. You don't have to simplify it. But one thing I would recommend that you get into practice of doing is doing the kind of algebra that I'm going to show. This actually simplifies, and it relies on you recognizing a particular factoring form, which is that if you have a squared minus b squared, it factors into this form: a plus b parenthesis times a minus b. So I'm looking at this expression here because if I can say a is equal to r2 squared and b is equal to r1 squared, then we can use this factoring form. And after we've done the factoring, I'm looking forward to getting this canceled out. So let me just write it out. I have 1/2 the one in the front that doesn't change times, now this expression factored out using this factoring formula, r2 squared plus r1 squared times r2 squared minus r1 squared. Now, this r2 squared minus r1 squared, it occurs here and here, so they cancel out. And this is how they got that weird addition of radii squared in the textbook formula. So, um, I guess if for no other reason, that it would be one reason to try this out, because it'll show you the derivation of the textbook formula. So that's it. That's this question. Depending on how you approach it, it can be super quick, just the way I did by looking up formula from textbook. But I would really recommend trying this approach as a way of kind of learning how to do this kind of question with not quite as much help from the formulas you would look up, which is the approach I've taken here, just to use the basic knowledge of rotational inertia of a disk, and the rest comes from the superposition principle, which is a very general principle that you are going to see many, many times in your physics and engineering education. So this is the next question. This question, I think, will illustrate a few things that frankly confused me when I was a physics student studying. So let me just jump right in. It says, marble rolls down an incline at, I have an angle, at 27 degrees from rest. All right, that seems simple enough. And it's asking for acceleration. Now, let me point out a trap that I think some people might fall into. If you are somehow remembering this formula for inclined plane problem, acceleration is equal to g sine theta. Let me tell you right now, that's going to be wrong. And it really comes down to the fact that this was a formula that was derived for a specific situation, a block sliding down an incline. the situation you have now is different. It's a subtle difference, but it is different. So if you are simply using a formula that was derived for a different situation, it's not going to work. And really difficult physics questions are like this question here, which is deceptively simple. And the job of a physicist or an engineer is to work through all the details of the situation, distill out what's important, and work out what the actual formula is. So let me do that. I like to start out with a diagram. So let me draw the diagram of the incline. Here's the incline at some angle theta. And I guess there's some kind of a marble that's going to be rolling down. All right. And it's asking for its acceleration as it rolls down. Because it asks for acceleration, it feels like it's a Newton's second law problem, because that relates acceleration to dynamical quantities. So let me start out with a free body diagram. If it's a Newton's second law problem, I'm gonna need a free body diagram. Now that we are dealing with a extended body, a rigid body, my free body diagram will start to include a little bit more detail. I still like to keep it as simple as possible, but one of the compromises you have to make is you have to kind of indicate size or sort of a geometric arrangement of the setup, because now where exactly the force is acting, it matters. So you can't simply draw a dot and say, oh, that's my object. You have to be able to indicate exactly where the force is applying. So I drew the circle as a representation of the sphere, the marble, and I'm drawing this dotted line as a representation of the slope, so that I can draw exactly where some of the contact forces are at. So this is same as any standard strategy. I'm kind of thinking through, all right, what are my forces? So there should be gravity on this marble. And this is the special property of center of mass. When you are drawing a representation of gravity on a free body diagram, you can draw it as if it's acting on that center of mass. And this is a kind of simplifying principle that you can prove mathematically that doesn't involve any approximation. This is exactly true. And what's useful here is that instead of kind of having to consider force on an extended body that's acting throughout the entire object, you can just draw one simple force that's at the center of mass. So, okay, there's gravity. And, oh, and there's going to be normal force at this point of contact. That's still normal, as in perpendicular to the surface. So normal force. Oh, yeah, and it's at this point where I want to point out a kind of a shortcut that I imagine a lot of people will be taking. And it gives you the right answer, so there's nothing wrong with using the shortcut. So let me outline that shortcut, and then I'm going to tell you why I won't be using it. And instead, I'll be taking the long route so that I can point out some of the things that I myself was confused with, many years ago when I was a fresh physics student. And I think it might confuse you when you're doing kind of a consistency check in the future. So I'm your instructor. I want to have the opportunity to point it out now. So first, the shortcut that you might be using. The shortcut is basically, it comes from realizing that when you are looking for this acceleration, you can relate that acceleration of this point here with kind of rotation about this point of contact, the pivot point. So if you have some angular acceleration about that point of contact, and you have that acceleration, then they are related this way. That distance there, that's the radius of the sphere. So the linear acceleration of center of mass is the radius times angular acceleration. So your goal is to find the angular acceleration. So, all right, so you look at this as the pivot point, and you see that, okay, normal force, that's generating no torque. the only force that's generating torque is this gravity. Okay, so this is my lever arm here. And you can go through the geometry to figure out what the lever arm is. Then you have your torque is lever arm times the force, and that's gonna be rotational inertia times angular acceleration. And I think one of the hints actually get at that this rotational inertia, you have to make sure that this is about the pivot point. It's not about the center of mass. So there's a rotational inertia of a sphere about its center of mass. And what you have to use is the parallel axis theorem to figure out, okay, what is the rotational inertia about this point? And once you figure that out, then you use that to solve for angular acceleration. Once you have that, you multiply that to r to get the linear acceleration. So that's the shortcut. You are welcome to do it that way. It'll give you a correct answer, and for the most part, it's conceptually correct. The reason I won't be taking that route is because having figured out the answer that way, this is what I hope if you spend a time with this situation, that what you'll be wondering is that, well, so you look at this free body diagram and you're looking at what forces are there, normal force and mg, and then you consider the net force. Well, net force gives mass times acceleration, and as far as the forces I have drawn here, they seem like they're the same forces that I have for mass sliding down an incline. So why wouldn't my answer be g sine theta? Why is that not the correct answer? So I hope you wonder that. And when you wonder that, what we have forgotten in previous analysis of this setup is that there is one more force. It's the friction force. At this point of contact, not only there's normal force, there's also friction force acting parallel to the surface. And in the previous shortcut method of analyzing this setup, I could just ignore friction force because this was the pivot point. Friction force provided no torque. So ignoring it didn't change my answer in any way. But as you're kind of thinking about this setup and trying to make it internally consistent, you should find that, oh, without this friction force, there's no way to make this setup internally consistent. And it's really this friction force that's what's slowing it down, so that the correct answer for this acceleration is smaller than g sine theta. And I think I mentioned this earlier in the semester, and it really ties to this statement that the marble is rolling, well, not down. I don't care if it's down or up. The fact that it's rolling. And I have alluded to this in the past, where I guess in the phrase of we try to neglect friction to the extent we can, except the situations where we can't. And when you have rigid body rotation, it's one of those situations where you can't ignore friction. Whenever you have a rolling motion, especially without slipping, you are going to need a friction. Friction is what causes rolling objects to roll instead of simply sliding smoothly. So I'm going to include this friction force in my analysis, and just so that it's not entirely redundant, let me do this in a slightly different way. So I'm going to use the full apparatus of a standard strategy, and so it'll actually be a bit of a long route. It's going to take longer than if you use the shortcut method, but this will help me fully justify the presence of that friction force and how that friction force explains some of the things that might have confused you as some kind of internal inconsistency. I did step number 1. I drew my free body diagram and included all the forces. Finally, I need to do step number 2. So that's defining my axis. It's the same usual axis, well, usual tilted axis, x down the slope, y perpendicular away from slope. That kind of goes with the direction of acceleration. All right, step number 2 done. Step number 3, I need to break down my forces into components. And the only force that needs to be broken down are the gravitational forces. So there will be this component here, y component, mg cosine theta. I'm kind of going through a little bit quickly because we've done this so many times. I hope all this sounds familiar. That's step number 3. Step number 4 is where I finally write down the mathematical expressions. And this is where I'm going to add some additional pieces from the fact that we are dealing with a rotational dynamics. So step number 4 is where I write down Newton's second law equations. And we are going to have the exact same pieces that we had before. We have net force along the x direction and net force along the y direction, giving the acceleration along those directions. So let me write those down. Mg sine theta minus the friction force is equal to mass of the marble times its acceleration. And the normal force minus mg cosine theta, the marble is now accelerating perpendicular to the surface, so that's equal to 0. And so this is where we would have ended up previously, before chapter 10, before rigid body rotation. And I hope as you do your unknown counting, you notice that you have friction force, acceleration, and normal force. 3 unknowns, 2 equations, not enough. And if you are somehow thinking that you could do, friction, that's friction coefficient times normal force, I hope you see that you don't have friction coefficient. And even if you did, you can't actually use that because this is technically static friction. So it's actually inequality. And so don't fall into that trap. Don't fall into that trap. It's static friction. So this is where you have to consider the rotation, and it makes sense. It's rolling down, so that has to be reflected in the mathematical description of the setup. So let me write down the rotational version of Newton's second law equation, which is that net torque. And so here it's a rotation about the center of mass. So both the normal force and gravity are providing zero torque because their lever arms are both 0. The only force that's providing torque is the friction force. That's why we had to include it. And the torque due to friction force will be the lever arm. That's radius of the marble, which we're not given. So I hope it cancels out. Times the friction force is the net torque. And that's going to be equal to rotational inertia times the angular acceleration. And this is the rotational inertia of a center of mass. And this is one sense in which this analysis is simpler than the shortcut I was describing because you don't have to use parallel axis theorem. You're considering rotation about the center of mass. We have angular acceleration. So one more unknown, only 3 equations so far. So need one more equation. And that's going to come from the fact that we are dealing with rolling without slipping. Sometimes we call this rolling without slipping condition. And that condition leads to this setup where I have this body, which is, let's say it's rotating with some angular velocity omega. Then the motion of the center of mass of V of that circular object is going to be related to omega through this relationship, R times omega. this is the relationship that ensures that this point of contact is at rest, so it's not slipping. And this relationship extends to all other kinematical quantities. So if you're looking at the displacement delta x, that's going to be equal to r times the angular displacement delta theta, keep on going above 2 pi. And if you have acceleration, that's going to be related to angular acceleration by r times angular acceleration. So there I can find, so that's my finally fourth equation that has no additional unknowns. So I have equations 1, 2, 3, and 4. Now, staring at this for a bit, I realized that equation 2 is kind of useless because it's giving me n normal force, and turns out I don't need the normal force anywhere. So I'm just not going to bother with the equation 2. So looking at equation 1, which contains the acceleration that we are looking for, if we just had a friction, that'd be great. So what I'm going to do is I'm going to kind of try to go through these other two equations, trying to solve for friction there, and then plug in into equation 1. So let me get right on that. I guess I need to plug in what the rotational inertia is. So let me do that. R times the friction force is equal to n. I have this memorized. You can look it up in the table for yourself. The rotational inertia of a sphere around its center of mass is 2/5 mass of the sphere times its radius squared. You don't have to have this memorized. It's going to be provided in a table. And when you look at the table, you will see that's the correct value. Times the angular acceleration, but let me plug in the result from equation 4 here. Solving that for angular acceleration, I get acceleration divided by r. So let me see what cancels. This r cancels, one factor of r there, and the remaining r cancels with that r. Okay, so I'm actually rid of all the r's. That's exactly what I was hoping for. Because I'm not given the radius of the marble. So it's one of those things that I wrote down. I wasn't given, but I was hoping it would cancel out. So let me solve this for friction force here. Friction force is equal to 2/5 times the mass times acceleration. Apparently, it depends on the acceleration, but this is the friction force that's required to produce enough torque to keep the thing rolling. And if some of the friction coefficient wasn't big enough to provide that, then you won't have rolling without slipping. So let me plug that in. Plugging that in, what I get out of equation 1 is mg sine theta minus the quantity we derived, 2/5 ma is equal to mass times acceleration. Let me breathe a sigh of relief and cancel out them because we don't know the mass of the marble. I was always hoping it would cancel out, as it often does when you are dealing only with the gravitational force. Let me collect the acceleration terms together. It's going to be plus 2/5 a. And I can just add this 1a, so 5/5a. So that's going to be 7/5 a. And solving this whole thing for acceleration, you get acceleration is equal to 5/7 g sine theta. So this 5/7 is the coefficient that's less than 1 and doesn't allow the answer of simply g sine theta to be correct. It has to be 5/7 of g sine theta. And again, the reason this is smaller is because of this friction force, which causes the net force along the x direction to be smaller. So yeah, so that's what I wanted to demonstrate. That's why I went the long route. For part B, you can do that pretty quickly. It's the kind of, well, it's exactly the same kinematics you've been dealing with. You have the acceleration. Hopefully you remember the kinematics equation. Change in position delta x is equal to 1/2 at squared plus v naught t. And here, initial velocity is 0, so you just plug in the numbers to get delta x. So it says bowling ball rolls up a ramp. Let me draw this picture here so that I have some concrete thing to imagine and have a thought of. It rolls up a ramp of some height. Okay, good. They are giving me the height. Oh, wait. What is its velocity at the top of the ramp? So at the top, I don't think it's at rest. So it has some height, h, and it says the bowling ball rolls up without slipping. So apparently, I have a bowling ball here, which has some initial velocity of center of mass. Let me call this VCM. And it has this odd phrase, without slipping. And this is a hint to you that a particular condition applies to this motion. That this is what your textbook refers to as rolling without slipping. That's covered in, I think, section 12.1. And under these scenarios, a particular condition applies. Because what you have to imagine is a circular thing moving in such a way that it combines two kinds of motions. It has this motion of center of mass, and it's rotating just enough that this point of contact has a velocity of 0. And under these conditions, what has to be true is that the angular velocity of this round object has to be equal to the speed of the center of mass divided by this distance here, which here would be the radius r. So when the question says it's rolling without slipping, it's telling you, use this relationship. The initial angular velocity of the ball is equal to its velocity of center of mass divided by r. And this condition will be enforced throughout the motion up until when it reaches the top and it's moving at some final speed v final. We would still have that the angular velocity final is the v final divided by r. So we need that. And I think that's the complete description of the setup. Now, you might be alarmed by lack of information on certain things. It's not giving you what the mass is. It's not giving you what the radius of the bowling ball is. So I'm hoping all those things will somehow cancel out by the time I getting to the answer for part A, and we'll see how that goes. So for part A, it's asking what is the velocity of the bowling ball at the top of the ramp? And as you stare at this situation, I hope you are thinking through what problem-solving strategy you can use. And I hope one of the first strategies that you will consider is conservation law strategy. If for no other reason, the reason you should consider conservation law strategy is because conservation laws are the easiest problem-solving strategy to apply. So there are questions that can be done using conservation law, but if it somehow can be done using conservation law, then you should use it because it's much easier than using standard strategy and then kinematics, or there are other ways to approach this question, but no other approach is as easy as the conservation law. So that's really the biggest reason you should consider conservation law strategy. And once you are there, then what you should think through is what are the conserved quantities? So far you have learned 3 conserved quantities. You've learned of conservation of energy, or more specifically mechanical energy. You've learned of conservation of momentum, and you've learned of conservation of angular momentum. And as you are thinking through this, there are conditions that you check. For momentum to be conserved, you need to be able to say that the net impulse due to external forces is 0. And here, as you consider this thing rolling up, that there are enough considerations here that tells you that, oh, there's a normal force here. And there's gravity here, and all that stuff are going to be changing momentum really horizontally and vertically. So the conservation of momentum is not going to work. And conservation of angular momentum, that's a little bit harder to see. But maybe one easiest way to see is that you can clearly see that your angular velocity will be changing. So somehow the angular momentum must be changing. If you are interested in the details, the thing that's changing the angular momentum in this case is the friction force that's applying net external torque that acts over time to change angular momentum. In the end, the important thing is to recognize that angular momentum isn't conserved. And after ruling out those two, I hope you can convince yourself enough that the total mechanical energy is conserved. If you are worried about the normal force and the friction force being there, the two non-conservative forces, with the friction force, this is a static friction force. It doesn't actually do any work because the point of contact here, where the friction force is acting, there is no displacement there. So this friction force, it does something special. It transfers one form of mechanical energy into another form of mechanical energy, but it doesn't do any work that would take out mechanical energy into other forms of energy. So again, the important thing is that you convince yourself that energy is conserved. Once you have that, then you can write down this expression that's the beginning point of all conservation law strategy problem solving. You say that the total energy at some useful snapshot, let me call this a snapshot 1. Total energy at that one snapshot is equal to total energy at this other snapshot. Let me call this snapshot 2. Total energy at snapshot 2. And then you break down the different parts of the total energy and you work through the algebra. So let me first do one thing that I think a really common mistake for people to make after chapters 8 and 9. So as you're writing down these expressions for total energy, it's easy for people to just write this. Say that, okay, my total energy at snapshot 1, no gravitational potential energy, I have kinetic energy. So 1/2 mass of the ball times V center of mass squared is equal to the total energy at the top. Now I have gravitational potential energy, mgh. And from the wording of the question, I feel like this won't be 0. So I have plus 1/2 mv final squared. And all of this might seem reasonable to you. You see that, oh, masses cancel out. And you work through the rest. And when you find VF through this relationship, plug in the numbers, get an answer, plug it in here, you will see that that's not correct. It's not going to be correct because you have forgotten something. You have forgotten a form of energy. And this is the form of energy we have to now worry about now that we have covered the chapters 10 and 11. We have to worry about the rotational kinetic energy. So let me explicitly write out different forms of energy that these things can have at different snapshots as you are considering those snapshots. So the total energy at snapshot 1, that's going to consist of the potential energy at snapshot 1, that's 0, plus the kinetic energy will have two parts. There will be translational kinetic energy, and there will be a rotational kinetic energy. And it's this rotational kinetic energy that we have forgotten in our previous attempt. And that is going to equal to the potential energy at snapshot 2 plus, again, the translational kinetic energy and the rotational kinetic energy. Oops, that should be 2. Kinetic energy 2, rotational. So I need to put these forms in. So I guess what this ends up being is, so at the top of the ramp, I think this, will this VF end up being higher than before? Somehow it might magically cancel out. Well, I'll have to see. I think when we do this properly, it'll end up giving you higher number than you might have previously thought. So the form of the rotational kinetic energy is it's analogous to the translational kinetic energy. It'll be 1/2 the rotational version of inertia or rotational inertia times angular velocity squared. Angular velocity at snapshot 1. And for snapshot 2, since if it has non-zero final velocity, it'll have non-zero final angular velocity. So this should be 1/2 the rotational version of inertia, I, times angular velocity squared. So that omega naught, let me just label that as omega 1 should be omega naught. So that's what I have to correct for. And now in this expression, you see a lot of unknowns. So let me substitute in some quantities so that we don't have, so that we correctly represent how many unknowns we have. One of those unknowns, the rotational inertia, it's something that you have to look up. And as you're looking up, you have to correctly note this is the rotational inertia about the center of mass. This is one of those examples where you break up this motion into translational motion of center of mass and the rotation about the center of mass. So when you are looking up the rotational inertia, it's going to be rotational inertia of a uniform sphere about its center of mass. By the way, bowling balls are not uniform sphere, but I'm going to assume it is so that I have a formula I can plug in. So when you look it up, the rotational inertia of a sphere about its center of mass will be 2/5 mr squared. So I'm going to plug that into these two terms. And for my angular velocities, omega naught and omega final, I had those expressions above. VCM over R, V final over R. I'll plug those in. So the version of this equation with all these quantities plugged in is 1/2 m VCM squared plus 1/2, 2/5 m R squared times VCM over R squared is equal to mgh plus 1/2 mv final squared plus 1/2 2/5 mr squared times omega final squared. So v final over r squared. And I hope as you stare at this, you see beautiful cancellations. Masses cancel out of every single term. So it's great. We don't need a mass. And another cancellation you get is radius cancels out. This r squared will cancel out this r squared. So you don't need to know the radius. The final result we get, it doesn't depend on the size of the bowling ball. So let me just write down the cleaned up version, and looking at the time, let me just leave it up to you to work out this V final here. So V final, let me write down the cleaned up version of this expression. Yeah, so 1/2 VCM squared. Let me just simplify this, plus 1/5 another VCM squared is equal to GH plus 1/2 V final squared plus, simplify this as 1/5 V final squared. So out of this equation, one equation in terms of one unknown, solve for the unknown, then you should be able to plug it in here. That's your answer. Yeah, and in terms of part B, if the ramp is double the height, does it make it to the top? You can approach it in different ways. I guess one way to answer that would be, you could just have all this expression and try plugging in h equals 1.4 meter. If the marble one or the bowling ball won't get to the top, in the solution step, at some point you might run into trouble, like v final squared wanting to be negative. That would be an indicator, oh, that height is too high. The bowling ball doesn't have enough energy at the bottom. The translational and rotational kinetic energy combined doesn't have enough energy to get to the top. So that might be one indicator. Another way you can do is you can do a different version of this equation. So instead of taking a snapshot at the top, you could take a hypothetical snapshot of the bowling ball at the height of its motion, where you can say that the kinetic energies are zero, and you can compare that maximum height with 1.4 meter. If the maximum height is greater than 1.4 meters, then yes, it'll make it to the top. If it's smaller, then no, it won't. So let me leave that for you to do as well. I mainly want you to point out this common mistake that people might make, not taking into account this rotational kinetic energy, and show you how to properly take into account of that. So cross product is, I guess, one of those things where, to a point, if it's something that you are struggling with, you feel like it's confusing and you don't get cross product, then I don't want to worry you, because we can get through this class 5 without understanding cross product. The number of topics that requires understanding of cross product small enough, you can get through the class without understanding cross product. So that's one perspective, and two, it's one of the things. If especially if you're taking physics 4B, it'll come up again, and it's a physics concept that, and applying the right hand rule, it's something that you will eventually have to understand. So why not now? At least why not give us an attempt now? So this is the first of those questions that I want you to do with cross product. uh, or do as an illustration of cross product. So it asks, what force must be applied to end of a rod along the x-axis? Let me just say this is my x-axis of some length in order to produce a torque on the rod about the origin. Okay, let me draw some of my axis. So that was my x. So this is going to be my y-axis, and my z-axis will be like this. So let's see. So you determine the direction of z-axis using cross product. So I'm having my hand. So this is how you do cross product. I recommend the whole hand version. You orient your hand in the direction of first vector x, which is going to right. You're right. And then I orient my hand until I can curl it in the direction of the second vector, which is y going upward. So I can curl my fingers from the rightward direction x hat to the upward direction y hat, my right hand. And when I do that, my thumb is coming out of the screen. So the three-dimensional coordinate axis is defined so that x cross y is equal to g. So the g-axis will be coming out of the board. So what they are saying is they want the torque about the origin to come out of the screen like this. So, and they're asking, oh, what should be the force? And this is where some practice with the cross product helps, because this is the relationship you are using. Torque is given by cross product of the displacement vector. This is the displacement vector and the force vector. So it would be easier if they gave us the force vector, because they already gave us the displacement vector. If they gave us the force vector and asked what is the torque, that would be easier, because then I can just do cross product with my hands going in the direction of r and rotate it until it's in the direction of f, and do the cross product. That's the direction of torque. because they gave us a torque, you have to do a little bit of a trial and error. So one thing, as you are applying right hand rule, it'll remain the same. Is the direction your hand is originally pointed at, and the only thing you do from there is rotating it to find the direction in which your fingers should curl, so that your thumb, which points in the direction of torque, comes out in the positive z-axis. And it looks like the way it would work is if my hand is oriented this way, so my um, uh, thumb is pointing out of the screen. In this orientation of the hand, I can do R cross F, and then the cross product is tau coming out of the work. So I can say my force, one of the possible directions for force will be upward direction. Now, it could be in other directions, but I have a sense they only gave us those choices, X, Y, and Z. So it should be in positive Y direction. And to get the amount of force, we just work through the magnitude formula. So the magnitude of torque is magnitude of displacement times magnitude of force times sine of the angle between them. And since my only available choices were either 0 degrees with this or 90 degrees, in this particular case, this is going to be equal to 1. So my force will simply be the amount of torque divided by the magnitude of the displacement vector. So 15 divided by 3.75. Yeah, and you see meters cancel out and you get Newton back. So 4 newtons in that direction. So that's one question dealing with cross product. And I guess, this is a multiple choice. You could take a guess and within 4 guesses be guaranteed to get it right. But right hand rule, it's a good tool to become familiar with this quickly. So let me look at the other question. So it says, yeah, so let me sketch out the situation while I'm reading the question. So it looks like I need to refer to some coordinate axis. So let me just sketch the coordinate axis first. And it's talking about a particle traveling along a line. So if I have my x and y axis this way, line that has a constant value of y is a horizontal line. So this could be a line where y is equal to 4.1 meter. So it's saying there's a particle that's traveling along this line. Oh, it has negative velocity, so let me draw it on this side, going that way. So let me say minus v, and my v will be positive value of 3.2. What is the angular momentum of the particle about the origin? Okay. So note how the question didn't give an exact position of the particle. It gave us y position. So that I can say, oh, that's a 4.1 meter. But the x position, it's a variable. It's just left it unspoken. Let's hope that it doesn't affect our answer. It's asking what is the angular momentum. So once we introduced cross product, and so when we were initially talking about angular momentum, we used this shortcut expression. Angular momentum is rotational inertia times angular velocity. This is done in analogy with the momentum equal to mv. Now, once we introduce cross product and properly state torque as being the cross product between the displacement vector and the force vector, then there's a way we can write or even define angular momentum in a way that stays closer to the analogy. Specifically this analogy. In linear dynamics, we had this relationship. Force was defined as rate of change of momentum. And within the rotational dynamics, we have an analogous relationship with the torque and angular momentum. Torque is equal to the rate of change of angular momentum. And once you have these two relationships, you are kind of constrained in saying how angular momentum relates to momentum. And it's this relationship. angular momentum is equal to, or maybe even defined as, it's defined as the cross product of the displacement vector with a momentum vector. So you can get the momentum vector here easily enough from knowing the velocity and knowing the mass. We can say the momentum, or minus of the momentum, is equal to mass times the velocity of the particle. And this is all in the x direction. That's the only direction the particle is moving. And it's a displacement vector. It's a function of time. One thing you can say is that it has this constant value of 4.1 meter for y, and the x value will be changing over time. So let's see if we apply this definition, it'll give us an answer where we don't need to know what this x is. By the way, there's a easier way to do it. Let me just state it for the record. You can use the concept of lever arm, and you can do angular momentum is lever arm times momentum. That'll work fine. Let me just use cross product here since I have it all written out. So we are doing this cross product between the displacement vector. Oh, I think I can write it all out. So x hat plus the 4.1 meter y hat, that's my r vector, cross product with the momentum vector, which is just minus mv x hat. It only has x component. And there's a kind of an algebraic property that you are used to using with the product you are familiar with. And what I will tell you as a kind of a guarantee is that whenever we call a new operation a product, it's because the properties you are used to relying on still hold. Things like a distributive property, they still hold. Commutative property doesn't hold anymore, so don't use that. But distributive property still works. I can distribute these two terms into this product. I can do one cross product at a time. So I can do x times minus mv. And then for the vector portion, I can do x hat cross product with the x hat. That's going to be 0 because they're parallel. Theta is 0, so it's going to vanish. So I'm left with the second term, which I'll do. So 4.1 times minus mv. So 4.1 meter times minus mv. I'll plug in those numbers later. And what we have is y hat cross x hat. And if you remembered that x hat cross y hat is equal to g hat, and when you swap the order of cross product, you flip the sign, then this is minus g hat. Two minus signs cancel out. And we have 4.1 times mv in the g hat direction. But I'm pretty sure this unit, I would consider that unit to be wrong, but that might be just my opinion. Joule, you shouldn't be using it unless you are dealing with the energy. But I think when it's momentum, it gets a little complicated. So I'll leave that one alone. So 4.1 times mass, 0.2 times speed, 3.2. I already handled the sign separately here, so yeah. And I guess so okay. From your perspective, R cross V. So thumb is pointing out. That is the direction of plus G. So I think that's right. Yeah, and that's your only choice anyway. There's no choice of minus G. 2.64. The basic SI unit. Yeah. Let me get started. It says disk of some mass and some radius with a small mass. Oh, I have two mass. Okay, let me call this mass of the disk and small mass. Oh, so it's gonna be important that it's a disk. It's gonna be important it's a small mass. Small mass of 0.3 kilogram. Attached at the edge is
edge is rotating at some value revolutions per second. So that technically that's not angular velocity, that is, or angular frequency. It is just frequency. Revolutions per second, that's the revolution like radians, it's not a real unit. But when we say revolution, one full circle per second, we are referring to frequency. The small mass, while attached to the disk, slides gradually to, so attached to the disk, slides gradually to the center of the disk. And it's worded in this specific way to make a particular thing hold true. So instead of having the small mass detach, we are having it actually move. Still attached to the disk, so it's still somehow interacting with the disk. So let me give a more detailed picture of this so that I can give a better, fuller description of this physical setup. So here's the disk of radius r, and there's a small mass attached to it. Let me draw the small mass here. And I said the small part was going to be important. I'm basically treating this mass as to be so small that I can treat it like a point mass. That's really what the thing is. And these are rotating together as some frequency, f, or you might be characterizing it with the angular frequency. Either is fine. Just make sure how you're doing it. And then it says, while this is rotating, this mass here, it's sliding inward until it reaches the center where that's gonna remain. So as you read that description, I guess, so you have quite a few tools in your problem solving toolbox. And whenever I'm not 100% sure what tool I should use, the first tool I would go to is conservation law. So really what I'm looking for is what quantity is conserved. And if I can find the conserved quantity, then that's the quantity I'll use to try to calculate whatever it is that I need to calculate. And I think as you are considering conservation law strategy, one thing that will help you are the fact that you only know of three quantities that are conserved. You know of energy, momentum, angular momentum that are conserved. So what you should go through is, okay, let's think through energy, momentum, and angular momentum. And go through the conditions for these things being conserved. So for energy, what you need to be able to say is no work by non-conservative force. And in this particular setup, I think that's a difficult thing to guarantee because it says that the small mass is sliding inward. And I don't think that's something that would happen without some sort of applied force, because usually as things are rotating, it could slide outward, but sliding inward, it feels like something must be kind of applying a force to get it to move inward. So that probably involves a violation of conservation of energy. And momentum, the condition for momentum being conserved is no impulse due to external force. And I think this situation kind of makes it difficult to conserve momentum. Kind of two reasons. So this force could easily be an external force. And there's probably a pivot at the center of the disk, which kind of applies whatever external force needed to keep it from moving around. So kind of go with the assumption that momentum is probably not the conserved quantity. So that leaves you with angular momentum. And if you somehow don't remember, the condition for conserving angular momentum is to rely on analogy between the linear motion and rotational motion. So with the momentum, the reason the external internal force distinction was important was because of Newton's third law. With the internal forces, you could rely on the action reaction force having equal and opposite impulse that would cancel out, so that conserves total momentum. Um, and so that's why if you have external force, that would now change the momentum. With so in the context of the linear motion, there was this kind of intimate relationship between force and momentum. And in fact, that was that rate of change of momentum gave you net force. In the rotational context, you're going to have the same relationship, which is that the torque, and same in the sense of there's an analogy between translational dynamics and rotational dynamics. And the analogy is this. Torque is the analogous quantity to force. The quantity that's analogous to momentum is the angular momentum. And as long as you have these analogies held up, then all the other relationships you had before is still true. All these other things equal to the rate of change of this quantity, they will continue to hold. So if you don't already know what the condition is for conserving angular momentum, then you look at what the condition was for momentum, and you kind of reproduce a version of that. So I guess we don't talk about rotational version of impulse. So skipping that, so all that no impulse means like a force acting over a duration of time. So so I have that duration of time in mind. So really what I'm getting at is no external torque. So as this mass is sliding inward, it's going to be interacting with the disk. So there will be some kind of torque on the disk. There will be some kind of torque on the mass. But those torques are internal torques. They are connected to each other through that Newton's third law. The action-reaction torque are going to be equal in magnitude. They'll cancel each other out. And this force that could be potentially external force, well, the lever arm for that force relative to this pivot point, that's 0, so that's not providing any external torque. So that's great. That one external force is not going to be producing any torque. So that after having gone through all this consideration is when you can figure out, oh, my angular momentum will be conserved. So now that I have a conserved quantity to work with, I can use conservation law strategy. So I've identified the conserved quantity. Then my quote-unquote second step is to identify a useful snapshot. Here, I think the snapshot will be snapshot 1, where the mass is out here on the edge, and snapshot 2, where the mass has slid to the center. Those are kind of the things that connect the things I know with the things that I don't know. So yeah, this will be F1, this will be F2. So those are the snapshots. So finally, or my third step, I'm going to write down the conservation law equation. Here, I'm going to use conservation of the total angular momentum. By the way, for this question, the vector property doesn't really matter, so let me use that. So, all right, so what I'm saying is that the total angular momentum in snapshot 1 is still equal to the total angular momentum in snapshot 2. And now, speaking of angular momentum, there are a couple different ways to express angular momentum. Yeah, and you can kind of review that. Those expressions are rotational inertia times the angular velocity. This is the version that's analogous to momentum is equal to mass times velocity. And there's actually one more expression that sometimes you need to know, that angular momentum it's connected to momentum through this displacement cross product with the momentum. Or you can think of this as lever arm times momentum. And these quantities are useful at different times. Well, what I would say just in the short amount of time is that this is the more fundamental expression. That's the kind of definition of angular momentum. But in a lot of situations, you would find this to be more useful. And that is the case, our case here, because with the disk and point mass, we can kind of figure out the rotation inertia relatively easily. And we are given the frequency, which is fairly easily related to the angular frequency. It's related to angular frequency by this factor of 2 pi. So let me use this expression here for angular momentum. So what I have is, all right, let me deal with the total rotation inertia. So in snapshot 1, I have a total rotation inertia at snapshot 1 times angular velocity at snapshot 1 is equal to total rotational inertia in snapshot 2 times angular velocity in snapshot 2. So I guess I need to write down what those rotational inertias are. So let me write them down. I'm going to use the superposition principle, which I mentioned before. So according to the superposition principle, the total rotational inertia in snapshot 1, that's going to be rotational inertia of the disk around the center, plus the rotational inertia of the small or point mass around the same axis. So for the disk, I know it's 1/2 mass of the disk and the radius of the disk squared. For the point mass at distance r, rotational inertia will be mass of that point mass times the rotational inertia squared. So that's at snapshot 1. And snapshot 2, this will be slightly different. So I still have the rotational inertia of the disk. That hasn't changed. What changes is at this, so when the point mass is here, it has 0 lever arm, so it has a 0 rotation inertia. So it'll just be 0. So it'll just be 1/2 mdr squared. So all right, let me plug those in and get the expression. So my initial angular momentum is 1/2 mdr squared plus mpr squared times omega 1 is equal to rotation inertia after the mass has slid to the center, 1/2 mdr squared times omega 2. So I have some things that simplify. Radius just cancels out, which is great because, it's great. I mean, even though I do have the radius, but hey, the fewer numbers I need to plug in, the better. And I guess with this angular frequency, you can, imagine plugging in the expression here. Then, this would be 2 pi times f1 given. This will be 2 pi times f2 that we are looking for. And the thing is, these 2 pi's just cancel out. So you could just replace. But this is the proper way to do it. So, all right, let me kind of simplify this here so that we can solve it for f2, which is what they're looking for. So solving this for f2, this is what I end up with. F2 is equal to, I have F1 times, I think it's going to be ratio of the masses, 1/2 md plus mp, 1/2 md plus mp, you can plug in the numbers, divided by this mass here, 1/2 md. And when you plug in the numbers, keep this still in the units of revolutions per second, you should just get the same unit answer. So yeah, so that's it. The really the most challenging step here is working out the one, kind of what strategy to apply and realizing that conservation law strategy can work and that angular momentum is conserved. Once you figure that out, then the rest is relatively simple.
So the question says, a bug flying horizontally. Okay, let me just start by, I'm just gonna doodle a little bit so that I have I can make sure that I'm reading the question the way I supposed to. Flying horizontally at some speed of v, collides and sticks to the end of a uniform stick hanging vertically. Okay, so I have some stick that's hanging vertically. After the impact, the stick with the dead bug on it, it swings out to some maximum angle theta. This angle theta from the vertical before rotating back. If the mass of, okay, so they're not giving me any numbers, but there's some symbol for the mass of the bug. And the question is saying the mass of this stick is 10 times that of the bug. Calculate the length of the stick. If after reading this question, it's puzzling you, you feel like you haven't been given all the information. I think that's perfectly valid. The thing that I think is really amazing about physics as a discipline is that the kind of the problem solving methods that we have, it allows you to really reason and calculate from limited amount of information. In other sciences, what sometimes we call stamp collecting, you gather a huge amount of data over which you don't need all of. In physics, really the sign of a skillful physicist is someone who needs a minimal set of information to work out salient points of an interaction. So, as you are looking at a question like this, we are now late enough in the semester where you have a lot of problem-solving tools in your toolbox. You have a standard strategy, you have kinematics, and of all those tools, what I would say is should be your first to go to are conservation laws. And the reason conservation laws are the first things that I would ask you to consider applying in any problem solving is that they are easy to apply. And one, and two, they are easy to rule out. In situations where they don't apply, it's easy for you to look for particular features of interaction and say quickly that, oh, this conservation law doesn't apply, let's move on. Because a lot of general problem solving techniques, they end up being kind of trial and error. So the kind of technique I want you to develop is how to fail quickly or how to try something quickly to know if it'll work and then move on if it doesn't. So here, with the conservation laws, one of the things that's nice is that you have exactly three quantities that can be conserved. You could have conservation of energy. That's a possible quantity to be conserved. You have conservation of momentum. That's another possible quantity to be conserved. And since last week, you have conservation of angular momentum. That's the third and last of quantities that could possibly be conserved in physics 4a. And I guess if you wanted to mass, but whatever. Energy momentum, angular momentum. Those are the three things you should consider. So with each of these, we should consider this interaction carefully and see if these quantities are conserved. I think it's relatively easy to rule out energy conservation. As you are reading the question carefully, it says sticks to the end of a uniform stick. And this sticks is enough important part. I hope that the phrase sticking reminds you of completely inelastic collision, where most possible kinetic energy is lost, and that's exactly what's going to happen here. So based on that, I'm going to rule out conservation of energy. That the way this interaction works, at least for the collision part, conservation of energy wouldn't work. Now, as I'm looking ahead to the swing up part here, I will say, oh yeah, energy should be conserved here. This is kind of like your ballistic pendulum lab. So where it asks about the momentum, and this is a bit of a tricky one. You have to remember under what conditions momentum is conserved. So if you watch through the lecture, the condition where momentum is conserved is when net external force is 0. Or, in the lecture, we had a bit of a refinement about the thing that we care being the impulse due to the net external force. So as you visualize this interaction, where I want to bring your attention to is this pivot point that's holding the stick. And I think it's good to have this imagination of how the stick would move if it wasn't being held here at all, that, and how it does move given that stick is it's being fixed at this point. And if you have an intuition that those two motions would look different, then that's good intuition. I want to encourage that. And yeah, they're going to look different. And because of that, I'm going to say at this pivot point, there's some kind of a pivot force. That pivot force will be our net external force. That's also going to be imparting some impulse during the collision. So once you get that far, then you reason, oh, momentum is not conserved because this condition doesn't hold. And the final thing that's left is angular momentum conservation. And I guess I hope that it holds. So I'm gonna move on. And you can make it hold. If you calculate the angular momentum about this point as the center, then whatever the pivot force is, it won't have any impact on conservation of angular momentum because it doesn't apply any torque. So with angular momentum, what you worry about is what is the net external torque. It's the similar condition as momentum, except we're talking about torque, not force. So in this setup, in the collision process, we can make it so that by choosing this as center of rotation, make the torque due to pivot force 0, and all other external forces like gravity are not going to be applying any torque during the interaction either. So that's kind of the hardest part, figuring out which quantity is conserved during the collision. Once you figure out the angular momentum is conserved, then the rest of the steps are a little bit easier. So we start out with, we write down conservation law equations. So this will be conservation of angular momentum equation. We choose some snapshots. We choose moments in time that will give us some useful equations. So I have a moment in time. I guess I can actually choose this as my moment in time, where I have the bug moving to the right at speed v. This is hanging at rest. So any angular momentum I have, it's going to come from this bug. So let me call this snapshot 1. And I have the other snapshot where the bug will have collided with the stick, and they'll be both rotating together. I can call them my snapshot 2. So as you are considering these two snapshots to write down the expressions for angular momentum, it helps to have a thorough memory of different expressions for angular momentum, because you all have seen at least these two different expressions. You have an expression for angular momentum that's built in analogy to momentum, rotational inertia times angular velocity. That's one. And that'll actually be useful for snapshot 2. But like with the snapshot 1, this expression can be a bit confusing because like what's my rotational inertia? What's my angular velocity for this thing that's moving horizontally?
and I think a more direct way to get at that is the other expression, actually definition of angular momentum. That is the displacement vector r cross product with the momentum vector p. And for this question, we don't really have to get into the whole vector nature of angular momentum. All we really need is the magnitude. And for the magnitude of angular momentum, we can say, all right, that's going to be rp sine theta. And I can kind of group together rn sine theta to say, oh, that's my perpendicular component of the displacement vector, or also known as lever arm, times the magnitude of momentum. And as you look at this picture, my lever arm is basically going to be this distance. Which is L. That's the, so this direction will be the direction of my momentum. And you look at the component of this displacement vector that's perpendicular to momentum. That's my L. So all of that to write down the relatively simple expression for snapshot 1, where the total angular momentum of the system is the angular momentum of the bug, which is the perpendicular distance, L. Oh, wow. I'm going to use lowercase l just so that I don't confuse myself. Capital letter is the standard letter for angular momentum. So it'll be the lever arm, lowercase l, times the momentum, which is mv. So that's the angular momentum in snapshot 1. The stick isn't moving, so it has zero angular momentum. Conservation of angular momentum says that should equal the angular momentum in snapshot 2, which should be the rotational inertia. Let me just give it a label, rotational inertia total, and I'll break it out into pieces in a little bit, times the angular velocity. That's how quickly it's swinging. So this is one equation. And when you are approaching physics questions, really what I encourage you to think through is think in terms of information and unknowns. Your information will be in the form of equations. I have one equation. Your unknowns will be the parameters that you don't know. So I have one equation so far. Let's see how many unknowns I have. I don't know this one. M, I don't know it, but I have a feeling it's going to cancel out. So let me just not count this as an unknown. V, that's given, so I know that. Rotational inertia, I got to write this out. Let me count this as another unknown. And angular velocity after the collision, I don't know that either. So I have so far 3 unknowns and 1 equation. That means I have to look for more information. I have to find more equations that will give me information that I'll need. So one thing I see immediately is, okay, this total rotational inertia, I feel like I should be able to write it out. So let me just give that a try. So the total rotational inertia, that will be, that's going to be the rotational inertia of the stick plus the rotational inertia of the bug. And this is where you might need to look up some formulas. Your textbook has table of rotational inertias. I'll just write down the ones that I have memorized. For a stick, that's a uniform rod of some length L with some mass 10m. And when you look up the formula will say rotational inertia of a stick is 1/3 times its mass. In this case, that will be 10m. Times the length of the stick squared. You have to be careful about which point. If it's about the center, then it's a different coefficient out in front here. If it's about an end point, that's where it's giving you the 1/3 formula. So I have that plus a bug. I'm going to treat it as a point mass. For point masses, their rotational inertia is their mass times their distance from the pivot point squared. So L squared. So looking at this here, I think I know everything, or I either know everything
or it's a quantity that I've already counted as an unknown. So, okay, so let me just do this as my second equation. Then I still have three unknowns and two equations. I'm making a progress. I just need one more equation. And this is where I think we'll run into a little bit of a snag, because we want to express omega. And you might think, angular velocity, I can relate that with the tangential speed, like omega is v over L, for example. If I know the end point is moving at some speed v, then that divided by L will give you omega. And this is where you could make some mistakes, like mistakenly confounding, conflating this V with this V. They are different, because the speed of the bug before the collision won't be how quickly this endpoint moves after the collision. So, so so I could, if I thought this would go somewhere, I could write down omega is equal to V final over L, but I don't think it'll actually go anywhere, because I don't have any leads on how to get this V final. So I have to kind of retract back and think more slowly on where I could get this omega. And this is where, unless you bring in some additional piece of information, you'll be stuck. You do need more visualization through the process, and you do kind of have to separate out this interaction from the collision, that's one, and the swing up. They are two different parts. In the collision was where angular momentum was conserved, and we used this. In the swing up is where you have to recognize, oh, that's a different interaction where energy will be conserved. So you have to write down an expression based on energy conservation. So that, because in the question, the information you are given is this theta. You need to have a plan to connect this information theta to quantities that you want, like omega. And it'll be energy conservation. So I gotta work that out. All right, so let me just work through conservation of energy. So this is a kind of like a pendulum, except more complicated, because it's not a simple pendulum. I have to basically think through the whole extended body of things. A portion of it is simple, the bug. Bug is being treated like a point mass, so the bug portion will be simple. But so as I'm considering this portion, with the bug at the end, the whole thing is swinging up at angular velocity omega. This will come to a stop at the highest position it'll attain, and the bug will still be stuck there, and I'm given this angle theta, and here omega will be 0. And so you think through it. I think for the snapshot A, I can, let's see. I think I should be careful here, because what I'm looking at is I'm looking ahead to snapshot B, where the kinetic energy will be 0, and so I'll have to look at what the potential energies are. And here the easy trap to fall into is say, okay, at A everything is kinetic, and at B everything is potential. So kinetic energy at A is equal to potential energy at B. And while there's a way to do that right, I think there are so many places where people can make mistakes. I'd rather just slow down and do this properly. Let me just define my reference point explicitly so that I'll be sure not to make mistakes. I'm going to use my pivot point as the reference. Let me just say my pivot point, that's where my height is going to be 0. And any other height references below that, I'll deal with it as a negative y. So I can kind of see where the bug starts and where the bug ends up. So, bug starts out from height of y is equal to minus L, and it's going to move up some distance to, and this is where you have to kind of start drawing triangles. Okay, this theta here is this theta here. So this side here will be cosine theta times this hypotenuse L. So at this height, my y will be minus L cosine theta. So okay, that kind of tracks the bug, and I can handle that. Let's see. Yeah, and what you have to worry about, I don't think you can ignore it, is the changing potential energy of the stick. So with the stick, I will just state this without proof and use it, which is that as far as the gravitational potential energy of the stick is concerned, you can use the center of mass of the stick, like that's where all the mass of the stick is concentrated. So this distance of L over 2, that's where I'll pretend the entire 10m of the stick's mass is. And it'll swing up to this position that's, L over 2 from the pivot point. So these distances will be y equals minus L over 2, swinging up to y is equal to minus L over 2 times cosine theta. All right, I think I've drawn enough picture of that to write out the rest. So for conservation of energy, I like to start out with this statement. Total energy at point A is equal to total energy at point B. It ensures that I don't miss something, I don't make a mistake in writing down some terms. And when I say total energy in this context with no springs, I mean the total kinetic energy plus the total potential energy in snapshot A. That's going to be equal to the total kinetic energy at point B. Oh, that's going to be 0. Plus the total potential energy at point B. So let me just write this all out one term by one term. Kinetic energy at point A, I think that's actually the easiest part. I can just write this as the entirely rotational kinetic energy. So I'll say that's 1/2 the total rotational inertia that I have up there times the angular velocity, this angular velocity here that we are still trying to find, squared. That's the total kinetic energy at point A, and all of this will include the bug and the stick, plus the potential energy at point A. Okay, I gotta write this separately. I have a potential energy of the bug. So the formula for potential energy will be mgy. This is my 0 reference, and I'm writing all my gravitational potential energy reference to that. And just as a care, make sure you are using the mass of the object. So bug, that has mass of m. The stick, it has mass of 10m. So potential energy in snapshot A for the bug, it'll be m, small m, g times minus L. That's its height. And the potential energy of the stick, that'll be plus 10 mg times minus L over 2. All of that's equal to the right-hand side. Kinetic energy was 0. So you only have to worry about the potential energy at point B. So that'll be the potential energy of the bug coming from this position here. Mg times minus L cosine theta plus 10 mg times minus L over 2 cosine theta for the stick. All right, I have that. Let's see. So this is my equation 3, where I've accounted for everything. Let's see if, so I know I have this unknown omega, which is nice because it'll connect to this new equation to the equations I've had before. And I don't think there are any other new unknowns. I mean, L is unknown, but that's what I'm trying to solve for. I already have that written down. And theta is a given quantity. And that's the nice thing. In this new equation, I'm connecting one of my unknowns to some of the known quantities. And I total, this is one of the unknowns that I've already counted that I actually have an expression for. So yeah, I think I finally have 3 equations and 3 unknowns. This is solvable. And this is the step where I guess traditionally I would have gone through another 20 minutes of algebra, which will be the end of the session. Let me take a shortcut. I think I can do this. I'm going to use SageMath as a proper computer algebra system. I think in previous lectures, you might have seen me use this as a basically glorified calculator. A computer algebra system is more powerful than that. It can do symbolic math. So let me use it as a computer algebra system. So I'm going to define the variables that I'll be using: lowercase l, mass lowercase m, speed of v. I think I need I total defined as a symbol. Need omega. Let's see. I already have I total. I don't think I need those written out. I need G, and I need theta. So those are all the variables I'm gonna be using. Let me write out my equations. I have my equation 1, L times M times V is equal to I total times omega. I have my equation 2 that will be I total is equal to 1/3 times 10m times L squared plus M times L squared. And my equation 3, that's going to be this last equation, 1/2 times I total times omega squared plus M times G minus L. I'm deliberately not simplifying things so that you can see the power of computer algebra system. All of the left-hand side is equal to M times G times minus L times cosine of theta. Cosine is a function, so you have to be careful about this parenthesis stuff. Plus 10 times M times G times minus L over 2 times cosine of theta. Okay, so I have equation 1, 2, 3. 13. Oh, yeah. Sometimes I think as I was entering it, the system did its own simplification. So, what I'm going to do is I'm going to use this function called solve. There's a solve function, and I'm just bringing up a documentation because I don't quite remember the syntax for when I want to eliminate some of the unknowns. So let's see there. I guess I don't have to eliminate. I can just give them as things to solve for. Yeah, so let me do it that way. So what I'm going to do is solve my system of equations. Let me enter that as array. Equation 1, equation 2, equation 3. It's got a lot of symbols defined in it. I want basically 3 unknowns. That's my L, I total, and omega. L is really what I care about, but I need to tell it to solve for I total and omega as well so that it knows which quantities are unknowns, and the system is going to assume everything else is a known quantity that I can plug in the numbers for. So they'll take a little bit of time. Most of that waiting time, like 2 seconds, most of that was initialization time. So now it's giving me a few solutions, some of which I can kind of recognize. Oh, that's a trivial solution. I don't want that, so I'm going to ignore that. It's giving me some other solutions. Okay, this one looks promising. Now, if this minus sign is discouraging you, look at this here. This whole quantity is negative overall, so this is a positive answer. And I think that's it. That's my second set of answers. That's not trivially true. So let me just say sol is equal to underscore. It refers to the previous output, and I'm just going to get the second element out of that. Yeah, that's my solution. And of the solution, I really only care about the first one. So solution, the
first one, not first one, sorry. That's the first one. That's what I care about. So let me plug in the numbers. And you can see that the m's canceled out as I was kind of hoping it would. I'm going to substitute in all the numbers I have. So I know G, that's equal to 9.8 meter per second squared. I'm just going to plug in all the numbers in basic SI units so that I don't have to worry about the unit conversion. I need theta. Now, the question gives me degrees. This program only accepts radian units. So I have to convert 7 degrees to radians by multiplying it by pi over 180. And I need a V, which is already meters per second, 0.45 meters per second. I think that's all the numbers. Oh, let me just put that answer through a function that gets me decimal approximation. It's trying to do this exact number thing, which I don't care for. Oh, wait, well, was there a symbol in there? Okay, that's a little bit weird. Not sure why it's claiming that's a symbol. Oh, I'm not sure. Let me just do it this way. I'm gonna. I think if I turn this into a decimal approximation, it'll just give me a numerical approximation. I'm a little confused. So, oh, I know why. It's because of this left-hand side. That's why it's thinking it. So let me do it this way, and because this will do what I want it to do. Okay, good. So the length of the stick is 0.0533 meter. So it should be 5.33 centimeter. So yeah, I mean, because it didn't save me too much. So 5.33 didn't save me too much time. Maybe save me 15 minutes of doing the algebra. But so the key skill that I want you to work on building is really what we did here, identifying what quantities are conserved, and based on that, coming up with these set of equations. Those are the steps that cannot be automated. There isn't a program out there that'll do this in place of a trained engineer or physicist. The step that we can automate is the tedious algebra. Computer algebra system can do it. Now, it's nice if it can also do it by hand, but, sometimes you get tired of doing it by hand and you want to automate it, and that's perfectly fine. That's what this SageMath is free. I think I've advertised it at the beginning of the semester. Around this point in the semesters where your equations kind of get complicated, so computer algebra systems really start to have its value, because this system of 3 equations for 3 unknowns involving squares and whatnot, it's the kind of thing that computer algebra system can do it with much less pain than doing it by hand. So, wow, that one question took a long time, and the hints say, which conservation laws apply, and I think it's bringing up all the points that I've already done. Yeah. Yeah.